Hello all, in this lesson we're going to be studying equilibrium. Here's your homework, copy this down. We're going to do part of them tomorrow and part of them the next day. And this has some pre-reading in it on Le Chatelier's principle. The aim is what is equilibrium, and this is your do now. Copy it down, but don't answer it. Equilibrium theory is on this slide. We already know that when two reactants collide effectively, that they might go through a reaction and form a new product. But could this happen in reverse? The simple answer is yes. And this relates to the concept of equilibrium. Equilibrium is when the forward and reverse rates of a process are equal. In a chemical reaction, it might look something like this. We have a system where two reactants are colliding and going forward to make two products. But these two products could also collide with each other and rearrange to go backwards and actually reform the original reactants. The symbol that we use to communicate to the reader that there is equilibrium happening, that it's not just going in one direction, but it's going in both directions, is this double-headed arrow. Fun fact about equilibrium is that although it is possible, it's not one of those things in chemistry where it's only theoretical and not possible. It only occurs in a closed system. A closed system is one where no amount of matter or energy can enter or leave. The reason why this is so important is because if the system were open, you would have particles entering from the outside and leaving the system permanently, and you wouldn't be able to reach equilibrium that way. Imagine that every time we went through a reaction going forward, one of the hydrogen molecules left the system. Then it wouldn't be able to, over time, it wouldn't be able to take the products and reform the reactants. So you have to be able to keep everything in place in order for the equilibrium to be maintained. Now, chemical equilibrium is one of our specific examples of equilibrium. So if you have in your notes a heading equilibrium with some stuff from the previous slide, this would be the first bullet. Let's take a look at this same equation from before. We have a methane molecule in the presence of water. Those two guys are going to collide, and they're going to make a hydrogen molecule and a carbon monoxide molecule. Likewise, the hydrogen and the carbon monoxide molecules can collide to create CH4 and H2O. Now, let's go through this slide. This is going to be mostly a thought experiment. When we first mix these two highlighted reactants together, the only reaction that could possibly occur is the forward reaction. The reason I say that is because for the reverse reaction to occur, this one, you have to have these two things present to make these. So these two things aren't actually present until they've been made by the forward reaction. So this is a dynamic process because as this continues to occur, you're going to notice that the methane and the water are both going to lower their concentration because they are reacting together to form these new compounds. So in this form, they're going to exist less and less often. The second part of this question asks what effect this would have on the rate of the forward reaction. So the forward reaction uses these two substances to make these two. So if the concentration of these two substances is decreasing, then they're going to collide less and less often. And if that's happening, then the speed of this reaction will decrease. All right, so the reaction's happening, it's moving forward mostly, so it's making all kinds of products here. It's making all kinds of hydrogen, all kinds of carbon monoxide. So the concentration of these two things are increasing, and that means something really important for the reverse reaction. As these guys start to be made more and more and more, their concentration increases and they're going to collide with each other more often. As these two guys collide with each other, there's a chance with each collision that they will break apart and reform these two. So As this reaction increases, you get more and more of these, higher concentrations of these two, and then they, in turn, will collide and create a reverse reaction to counter the forward reaction. All right, so this has been a lot of words. I am going to give you an alternate explanation for this using a diagram, and I want this diagram copied. Okay, so at first we have here's our chart. It's concentration versus time. And at first we have a large concentration of the CH4 and the H2O because that's all there is in the beaker at first, so that's high concentration. And you have a super low concentration at nothing for H2 and CO. However, as soon as these two guys start to collide, they start to create these two guys. So you're going to see the concentration of this fall while the concentration of this one rises. So the lines are starting to flatten out, and we need to be able to explain why that would occur. So here's the reason why. As the CH4 and the H2O react, they create more of the H2 and the CO. So that's why you see that these guys' concentration are increasing and theirs is decreasing, but there is a flipping point for that. Because once you've made enough of this, you're going to start to see these two react and start to make those guys. So that's going to slow down the rate at which the product is formed. So you're going to see this start to flatten out, and this process flattens out as well. Now, eventually, the rate of the forward reaction is equal to the rate of the reverse reaction, and you'll get these flat lines. You could also think of these flat lines as being constant concentrations. However, it is not true to say that the concentrations are equal. You can see in the diagram that the concentrations are in fact different, not equal. All right, so let's get rid of this. I just wanted to make sure that you guys pick up on this last bit. Chemists actually never consider reversible reactions to ever stop. Instead, we just believe that the rate of the forward and reverse reactions become equal. And when the rate of the forward and reverse reactions become equal, you would not notice any changes occurring. I have an analogy to help you guys think about this. Let's say that you are a mile up in the air, like just a mile up in the air, and you're looking down on Times Square. It looks pretty crowded, right? Let's say it's a crowded day. And every 5 minutes, the police allow 1,000 people to enter Times Square. And they also allow 1,000 people to leave. If you're a mile up in the air, you may not notice the 1,000 people leaving and the 1,000 people entering. In fact, you might think that nothing is really changing because the number of people in Times Square would actually stay the same during that time process because the number of people entering and leaving are equal. So that's the way chemists think about these reactions. We don't think reactions ever stop as much as the rate of the forward and reverse reactions become equal. However, remember, it's the rates that are equal. It is not their concentrations or their amounts that are equal. It's only the rates that are equal. I will highlight that just to underscore its importance. So highlight that yourself or copy it down. Phase equilibrium is a form of physical equilibrium rather than solution equilibrium. And it's really easy to understand. In a phase equilibrium, you have a liquid. It sends up some vapors. But if the system is closed, the vapors will just keep floating around, maybe return to the liquid. And at some point, the number of particles evaporating becomes equal to the number of particles condensing. And there you have your phase equilibrium. So let's make this practical. We need to write down an equation for the solid-liquid equilibrium of H2O. So this is the melting/freezing equilibrium. We use that double-headed arrow. There's my solid, and here's my liquid. Done. Now let's write an equation for the liquid-gas equilibrium. We're going to need our double-headed arrow again. Here's my liquid water, and here's my gaseous water. So what is equal during phase equilibrium? It's certainly not the amount of liquid water and the amount of gaseous water. Instead, it's the rate at which liquid turns to gas and gas turns to liquid. That's what's equal during phase equilibrium. But we know that there is actually rarely a permanent equilibrium between the phases, and the reason is because it actually is very difficult to keep a closed system for energy. For matter, it's not too hard, but for energy, it's really difficult to close the system. Here's an example. So here's my example. Even the best cooler in the world, if it's full of ice, could not be a closed system. It could probably keep matter from coming in and out, but the cooler does its very best job of keeping the heat from coming in and melting the ice, but it can't do a perfect job because the cooler itself is made of atoms, and those things just leak energy. All atoms are conductive to energy to some extent. So even the best cooler in the world over time would melt the ice. So there really is no such thing as a closed system because all matter will leak energy. Solution equilibrium is pretty easy to understand as well. Here is a group of ions which has just been dropped into a solvent, and all of the ions want to dissolve because there's nothing up here already dissolved. So at first, that's what you see. At first, you're going to see mostly particles dissolving, going that way, but you will start to see some particles head back to the crystal. And when you get to this third stage, you'll notice that you have equal numbers of particles dissolving as you have recrystallizing. So when those two processes become equal, the recrystallization and the dissolution, that's when you've reached a solution equilibrium, which we would call saturated. So that answers the first question. Diagram 3 is the one that shows our solution in its saturated state. And remember, solutions that are in their saturated state are in equilibrium between the dissolution and the recrystallization phases. So here's your pair up. Please copy down these questions. And here's your summary. Just get the gist written down. You don't have to write the whole paragraph. But again, don't answer it. And thanks for watching. I hope you have a great evening.